This radiation heat transfer example problem is going to involve finding a shape factor, and to do that, we're going to use the summation rule. And the summation rule essentially says all of the radiation leaving a surface has to go somewhere. Doesn't matter where it goes, but if you add up all of the possible destinations that it could go, all of those shape factors have to add up to 1, which is 100%, since a radiation shape factor is a percentage. And in this video, I'm going to be using terms shape factor and view factor interchangeably because they're the same thing. Sometimes it's called configuration factor or angle factor, but I'll stick to shape factor and view factor. So in this problem, we've got a cylindrical pipe, and we want to find out how much heat transfer is going to be emitted through the inside of that pipe and that is going to hit the disc that's over on one side. So I'm going to start off by grabbing an equation from the FE reference manual, net energy exchange by radiation between two black bodies. So I'll go ahead and write down an assumption. I'm going to assume that these are both black bodies, which is a really good assumption to make for most radiation problems. So if you can make it, if the problem doesn't specifically say you have gray bodies, assume black bodies, makes the problem easier. So Q dot equals area times shape factor times Stefan-Boltzmann constant times the difference of the fourth powers of your two temperatures. But I should throw a couple other assumptions at this problem first before moving to the shape factor, and that is that I want to ignore convection. I'm only looking at radiation heat transfer because I'm not given any information about the air in the area or whether it's moving or stationary, right? Natural versus forced convection. So let's look at just radiation. And then from thermodynamics, steady state. That's almost always a good assumption to throw in there. If I want temperatures to remain constant, which I definitely do, then that means assume steady state. So plugging in numbers that we already know, who knows, maybe it'll be just a plug and chug. 300 to the fourth, 1000 to the fourth, right? These temperatures have to be in Kelvin in this equation. The Stefan-Boltzmann constant is a constant, 5.67 times 10 to the minus 8. And we can figure out the area of the emitting surface, right? The inside of the pipe as the circumference of the pipe times its length. So pi times d is the circumference and then the length of the pipe. And that leaves us with just one term to find, F12, which is the shape factor, which of course seems like we're really close to the end. We just have to find one thing, but this is like the whole problem is determining the shape factor. Right? Finding this heat transfer at the end, this is just the little plug and chug part. So when you need to find a shape factor, go into your textbook. There's going to be some sort of table or figure that has a bunch of common sort of shapes, squares, cylinders, discs, rectangles. And just see if you can find your scenario in the table. And of course, this scenario is complicated enough that it's definitely not in there. From a cylinder to a disc, no way. But we can get kind of close. We do have a table entry for two parallel discs. And in this problem, that's going to look like A2, like the destination disc, and A3, the entrance to the pipe. So let's go ahead and solve for this shape factor. From the disc to the entrance of the pipe. And I know that this isn't actually, like I'm trying to go from the pipe to the disc. So this is kind of backwards, but remember with shape factors, it's okay to find the shape factor in the other direction than the one you need, because you can always use the reciprocity rule at the end. And based on your two cross-sectional areas, if you have the shape factor going one direction, you can reverse it to get the other direction. So it doesn't really matter which direction you start. All right, so from my table, I'm gonna label my two discs here, A2, right? I'm gonna call this actually R1 just to match what's in my table, and then R2 will refer to A3. So both the radiuses are 0.1, and my H, the distance between them is 0.2. So I find capital R1 is 0.5, capital R2, 0.5. Plug this in to find X, and that's gonna be a value of 6. And then plug X, R1, and R2 into this shape factor equation. And yeah, this is kind of a big equation, but trust me, it could be a lot worse. Some of these shape factor equations are really bad. This one's medium bad. Plug it in, shape factor 0.1716. So 17% of radiation emitted by the disk will enter the pipe. Or oppositely, 83% that emits from the disk would just go off to the sides and just miss the pipe entirely. So next, if we're interested in what happens inside the pipe, now we can start talking about the summation rule. So all of the energy that enters the pipe through A3, there's only two places it can go. It can either hit the walls of the pipe, which are A1, or it can pass completely through the pipe and exit through A4. So A1 and A4 completely surround A3. So by summation, we can say that F23 is equal to F21 plus F24. So all of the radiation from 2 that enters at 3 either hits A1, so that would be F21, or it leaves through A4. That would be F24. That's it. There's no other possibilities. Now, this isn't all the radiation leaving A2, right? Some of it, the 83% could just escape just out to the middle of nowhere. But for only this 17% will be divided by how much hits the wall and how much leaves. So the reason this is good news is that even though I can't calculate how much hits the wall directly, I can calculate how much leaves through the far end of the pipe A4, because that also is just another regular disk shape. So the same way I solve for the disk A2 to A3, I can solve again A2 to A4, right? How much emitted by A2 would pass all the way through the pipe at A4, basically just shoots straight out to the side. So my two radiuses are still the same, 0.1, but I now have a longer value for H, 0.4. This makes my capital R1 and capital R2 terms smaller, only 0.25. My X term ends up bigger, 18, and then plug into the F equation for the shape factor, get a shape factor of 0.05573. And it makes sense that it should be smaller, right? Because a lot of the energy that enters A3 will hit the pipe. A smaller amount will pass all the way through. And so by the summation rule, the amount of energy emitted from disk 2 that hits the side of the pipe is equal to the amount of energy that enters the pipe, F23, minus the amount of energy that leaves the pipe through the far side, F24. So 0.176 minus 0.055. I get my shape factor from 2 to 1 from the disk to the inside surface of the pipe, 0.1159. And as I said at the very beginning, reciprocity rule means that you can switch the direction. So area 2, F21, is equal to area 1, F12. So for area 2, that is the disk, its area is the circle, pi r squared. Area 1, which is the pipe, the inside of the pipe, is surface area of a cylinder, circumference times length, so pi times diameter times length. So this ends up getting divided by 4 when it reverses, so F12 is 0.029. So if the disk emits energy, 11.59% of it will hit the pipe, but when the pipe emits energy, only 2.9% hits the disk. And this is because the pipe has a lot more surface area. So from the perspective of the disk, it has a pretty big field of view where it can hit the pipe. But from the perspective of the really big pipe, the disk looks a lot smaller over there on the side, which is why its F is a little bit smaller. And just to double check conceptually, if we just think now of the inside of the pipe emitting heat, where is that radiation going to go? Well, half of it is going to go off to the left, right? The disk is over here on the right. Half of it is going to go off to the left. So guaranteed, only half, only 0.5 of the radiation is even going to the right side at all. And a lot of that radiation, most of it actually, is just going to hit the inside of the actual pipe. So only a small amount of the radiation is actually going to leave through the hole at the edge of the pipe. But even some of that radiation is going to still miss the disk entirely. So it's really only a really small amount that goes first 50-50, which direction will it go? And then it has to fit through the small hole in order to leave the pipe. And then it has to be aimed perfectly to still hit the disk without passing above or below it. So a very small value, 0.029, does seem realistic. We would expect this to be a pretty small, a low percentage. And with that, this is finally a plug and chug problem. I can throw this 0.029 back into my net energy balance by radiation between two black bodies equation, and I get Q dot equals 205 watts. So 205 watts are emitted by radiation from the pipe to the disk, and that ignores convection. That's only radiation energy. Radiation is probably the last topic in your heat transfer course, so final exams are coming up. Click on my heat transfer playlist. It's up on the screen now, and bookmark it for later. You don't have to watch any of the other videos. You got other stuff to do now, but if you bookmark the playlist, when it comes time to studying for your final, you'll be able to pull it up and see every video for the whole course just for real quick access to refresh your memory before the final exam.